Given Earth's mass of 5.97 times 10 to the 24 kilograms, the moon's mass of 7.35 times 10 to the 22 kilograms, and that the distance between the centers of Earth and the moon is 3.844 times 10 to the 8 meters, how far above Earth's surface is the force of gravity 0, given that Earth's radius is 6.37 times 10 to the 6 meters? Assume that the Earth and moon do not themselves move to simplify matters. So we're assuming a stationary Earth and moon. So let me kind of draw a sketch of this situation. This is actually a pretty difficult problem, I think, and we may not have space to show all the math details. So I'd like to kind of focus on the setup more for this one. This one definitely is pushing the envelope a little bit and probably would not be an exam question unless I just wanted you to spend the whole time doing this one, I guess. Anyways, and you'll see how the math turns out, why I'm saying that, I think. But if I kind of say, okay, like, hey, maybe this is the Earth, and it has, I'm just going to put m sub e here for its mass. Here is the moon, and I'm going to put m sub m there for its mass. Hopefully that kind of makes sense. And then I'm kind of establishing variables here because I'd like to be able to write equations, and these numbers have all these powers of tens and units and everything else. So working with them is going to be a little bit cumbersome. So instead of doing that, I like to establish my variables here and work with those instead. And I'm just going to say that the separation between the centers of the Earth and the moon, I'm going to label that as an R. And then I'm going to imagine that I'm placing some other mass. And I think it's probably going to have to be farther from the Earth and closer to the moon, but somewhere between the two of them. When it says there, how far above Earth's surface is the force of gravity 0, we're talking about, like, if you put an object there. Like, where would the force of gravity be 0? And why might there be a spot where the force of gravity is 0? Well, there's got to be, at any point, the Earth is pulling that object to the left in this picture, and the moon is pulling it to the right in an attractive kind of way. So we're looking for the spot where those two attractive forces exactly cancel out. That's really the goal here. To establish maybe a variable that's going to be useful for me to solve for that, I'd like to say that the distance from the center of the Earth to this object, I'm going to label that as the variable x. And I'm going to basically see if I can set this up in a way that I can solve for that variable x. And then something I'm going to have to remember to do is, though, if I find the value for x, does that answer the question? The answer is no, because the question is how far above Earth's surface, whereas x is from the center of Earth. So I'm going to have to subtract an Earth radius from whatever value of x that I get in order to actually get the correct answer. So hopefully I will remember to do that. But if I look at this situation, and maybe maybe I can draw a little free body diagram and say, hey, like, what's going to happen here? There's going to be a pull that the Earth, and maybe I'll just put F sub e here for Earth's gravitational pull on the object. And then in the opposite direction, there's going to be the pull of the moon. So I'm just going to say F sub m for the pull of the moon there. And the idea, of course, is that if the net force on this object is equal to 0, that suggests that this pull of Earth's gravity should be equal. I think this makes sense, right? The spot where essentially there's 0 gravity is going to be where the pulls of the gravity due to the Earth and the moon, respectively, are equal magnitude to each other but opposing directions. So let me see if I can write some expressions for that in this space over here. I think I'm going to wind up needing it. Now, let me see. Actually, before I do that, let me make sure I've established all my variables here. So recognize we have the mass of the Earth, because we might need this if we're going to, actually calculate something, even though, like I said, I'm probably not going to be able to show all of that. But just recognize, in terms of my variables, there are numbers behind everything, right? So, in other words, I'm going to use m sub e to mean the mass of the Earth, and it's going to be equal to 5.97 times 10 to the 24 kilograms. I'm going to use m sub m to mean the mass of the moon, and that's going to be 7.35 times 10 to the 22 kilograms. I also, this r I'd like to refer to, but I have a number for that as well, so I may as well write it down and say that, r is equal to 3.844 times 10 to the 8 meters. So I've established those kind of three things. And then based on that and the unknown variable x, and that these two forces must be equal to each other, I think I can express that by stating, okay, law of gravity, oops, that was meant to be an M sub E. This is, I'm applying the law of gravity to the pull of the Earth on this object, where if that object has a mass m, and of course me is the mass of the Earth, and then the distance between the centers of those two is the variable x, so I'm just going to put x squared in there to represent that. So I'm kind of doing this equation right here, and I'm doing the left side of it right now. And now I'm going to put the right side on the other side, which is the pull of the moon. And the pull of the moon, I think, is going to involve the expression of Newton's law of gravity with the mass of sort of, maybe I could put a little a label m there for sort of my test mass in this situation, whatever it might be. It's being pulled by the moon, so that's the other mass that's going to be here. And the thing that I'd want to put downstairs in this inverse square law is the distance from here to here, which I didn't establish a variable for that, but since the total distance between the Earth and the moon is r, and the distance from the center of the Earth to the object is x, I think it stands to reason that this can be r minus x would be the magnitude, and then we'll just square that. So this is kind of my starting place here. And again, it was based on the net force being equal to 0, or, you know, really like these two contributions to the gravitational force canceling out. I'm going to cancel off, oops, that one kind of missed a little bit there, but I'm going to cancel off the common factors of the gravitational constant and the mass of the test mass, which really shouldn't matter, right? That simplifies things a little bit. And then I think I'll just write over here, if I cross multiply things, I would get mass of the Earth multiplied by r minus x squared. And on the other side, make that equal sign a little bit better, I'll multiply the x squared, so I'll get mass of the moon times x squared. So like I said, things are looking pretty mathematical here. We'd like to solve for x, right? So again, our goal is solve for x. Looks easy, right? There's a bunch of squares and stuff here. I think what we're going to have to do is we're going to have to kind of multiply out, I think, this kind of binomial statement right here, r minus x squared. We're probably going to want to subtract the m sub m x squared to the other side. And what we're going to wind up with is a quadratic. And instead of showing all those steps, I'm going to write the result. It's kind of long here in standard form for a quadratic. So if you wanted to get some practice, and maybe it's optional, because in all honesty, in this class, I don't really want to emphasize, certainly in like assessments in this class, like being able to solve tons of quadratics is not necessarily that huge an emphasis. I mean, I wouldn't necessarily promise it would never come up, but it's not as huge an emphasis as understanding the concepts and how to set things up, which we've kind of already done here. I mean, that reasoning kind of happened once we got to this line right here, and at this point, we're just kind of grunging through this math here. And boy, this sure is some grungy math. And again, that's why I'm not going to wind up showing all of it. I simply don't have the space. But what's cool about this is I've now got this quadratic in standard form, and that means I can use the quadratic formula to solve it. And the way that that might turn out, you might recall it's like negative b plus or minus, etc. But let me see, start with that negative b would be this part, right, the part right here in front of the x, which would be, it's negative that, but it's already minus, so it's just going to be a positive 2 m e, whoops, and don't forget the r that's there. And then it would be plus or minus square root of the, what do they call it in math? The discriminant, I think, right? Anyway, something like that. And I think it would be 4 me squared r squared. I'm really just squaring the same, this would be the b, right? B squared minus 4ac is what you usually do. And let me see, 4ac, so I'll do minus 4. A is all that thing, right? So I'm going to put me minus mm, and then it was ac. C is all of this right here, the whole constant term. So it would be me r squared, and then I need to extend this square root to include all that whole thing divided by 2a. So underneath this I will write 2m, whoops, e minus mm. one thing possibly worth discussing is there's a plus or minus here. So what do? One option is to calculate both numbers and then just figure out which one makes sense. Here's what I think is going to happen. I think if you calculate the plus number, you're going to get an x value that's larger than r. And what that corresponds to is when we stated that these two forces are equal, expressing the fact that the net force is equal based on this free body diagram, the math doesn't really understand that if x is large enough that the test object would be on the other side of the moon, that actually there the force of gravity from the moon has switched directions. Again, the math doesn't really understand that. In that sense, the math is just saying when are these two forces equal? And there's another spot over there somewhere where the force of gravity due to Earth and the moon are equal. However, they're pulling in the same direction, so that spot doesn't count. Again, the math doesn't get that. A human being can get that. So that means I'm going to want to cross away this plus because I think that's what that solution actually corresponds to. The minus solution, I think, will give us a value for x that's somewhere between 0 and r, and we can calculate that. And I've gone ahead and already calculated that ahead of time, and maybe without too many sig figs held back. I'm just going to write down this big expression here, try not to miss any parts of it. Let's see, 848. I even had a point 2 here, and that should be in meters, okay? And then I should subtract from that. I'm just going to put a subtraction. I'm going to do this in my calculator again. I'm going to subtract that Earth's radius because we've got this solution for x, but we've got to remember that doesn't actually answer the questions. We've got to subtract the distance that the surface of the Earth is from the center of the Earth, and I'm just going to write this in this kind of weirdish way. And then I put that in my calculator, and I get a number that's like, oh shoot, how big is that even? I don't know, it's like 339 million, I think, 637,848.2. But I think that one I can safely, I'm just going to write it in scientific notation at 3 significant figures. That's 3.40 times 10 to the 8 meters. So like I said, I'm running out of space here, and I've not shown everything there. But that is a result, and I'm going to go ahead and check it. There it is. It also mentions, though, that based on the moon's equatorial radius of 1738 kilometers, this is just 3.67 times 10 to the 7 meters from the moon's surface. And you might say, well, okay, what does that mean? Keep in mind, so this number is maybe a little bit more than a tenth of this number, which means in reality, my picture is probably not scaled correctly, and I think this mass should actually be a fair bit closer to the moon than was shown here. But again, that was just my guess in my starting sketch to set up this question. So hope you've enjoyed this, and have fun working through all that math if you want to. But again, it's optional. Just make sure you understand kind of where the ideas came from.